In this video, we'll try to cover memory management. Usually, memory management will be divided into two modules, especially according to VTU syllabus. First part of the memory management will be last portion of module 3, and last part of memory management will be first portion of module 4. So this portion, memory, virtual memory, background, page replacement, allocation of frame and thrashing, is already given through video. So this part we'll try to cover. We'll try to divide this part into two videos and we will cover. So first we'll start with memory management. Why actually memory management is required? It is because memory size is very less. So we cannot fit a very large program in the main memory. So what has to be done for that as a solution is actually virtual memory. We should keep a backing store, or we should keep a virtual memory where we can actually store the programs, and whenever it is needed we can bring it to main memory and execute. But that part actually we will discuss in the last part of the memory management. So as of now we will see what is the technique used to solve this problem. That technique is called overlay. That technique is memory management strategy. The technique is called overlay technique. What is overlay technique? That overlay technique we will see in this. Overlay actually comes as memory management strategies. Okay, in this strategy we can actually fit larger size program in main memory. Larger size means when the available memory is very small, we cannot accommodate available memory. We don't have sufficient memory space to accommodate the program. So how we solve that problem, that will be discussed in memory management strategies. And memory management strategy, first strategy is nothing but overlay. Overlay is actually a technique where we can fit some program whose size is larger than the memory size. Okay, first we'll describe through diagram. Just see this scenario. This is an assembler assembler will execute in two pass 1 and pass 2. Pass 1 length is 20k, pass 2 length is 40k, pass 2 length is 20k. Symbol table and common routine is 20 and 30k. Okay, so as of now consider one situation where I have only this much of memory space available in the main memory. How much memory? I have taken one line equals to 10k. So I have 40k memory available. And how much actually this together, how much it takes, how much is the size? 40 plus 20, 60 plus 20, 80 plus 30. So 110. 4 plus 2, 6, 8 plus 3, 11. So 110k it is required. How much memory I have totally available? Just don't consider anything inside. Just consider this is the free memory I have. So how much memory we have? 50 plus 10, 60 plus 4. So 100k memory I have available, where I need to fit 110k of program. Is it possible? It is not possible. To take as a solution, what overlay follows is, there is a driver called overlay driver. Okay, overlay driver doesn't come with the operating system, so we need to install the overlay driver, which takes 10k of memory. What it does actually, see, pass 1 and pass 2 both need symbol table and common routine for execution, but the funny thing is pass 1 and pass 2 does not execute together. So what we need is, we need these both to be together present in the main memory, and at a time we need either pass 1 or pass 2. So what we can do is, overlay driver can do is, it can load only these two, symbol table and common routine, and in the available free space I can accommodate pass 1 and pass 2, either pass 1 or pass 2. So whenever pass 1 has to be loaded, it takes 40k, and I have exactly 40k memory space available. So pass 1 we will load and execute, then we'll remove pass 1 from memory and we'll load pass 2 needs only 20k, so half of the memory available. So with the help of overlay technique, we can accommodate a program in the memory whose size is larger than the main memory. Now the question is overlay, for working with overlay we need a driver, so that takes also some memory, that is suppose we have imagined it is 10k. So you may feel that 10k is some extra memory we are taking. No, actually it is true we are taking, but our pass 1 pass 2 size will not be so small. Maybe pass 1 will be 100k and pass 2 will be 200k, and I have available memory only 100. I have only available memory 200k. So for 300k I can manage with 200k. Like what I am trying to say is, see, I have 200k memory available and my pass 2 length is 200k and pass 1 length is 100k. So I can fit pass 2 easily. So I am saving 100k. So actually originally it will not be so less, like 20k, 30k. So 10k overlay driver is a negligible amount I try to mean. So overlay is a technique by which we can fit a program whose size is larger than the main memory. So it is one of the technique to manage the memory. It comes under memory management strategy. So after memory management technique, we will go for the next topic, that is swapping. Background is all the necessary things I told. So next we will go for swapping. So if you want to cover swapping, we should see this is a CPU, this is main memory, this is virtual memory. Virtual memory size is very big compared to main memory. So what we need to do is, we cannot fit all the programs present in virtual memory to main memory. Virtual memory is nothing but your disk, hard disk, where you store your program. So all the programs, as it is a large memory, we can store in virtual memory. But why we need virtual memory? Because memory size is small. And why we need to have the program in main memory? Because CPU is the main executor. CPU will be executing the program and CPU is connected with main memory. So if the program is present in main memory, then only CPU can execute the program. So at the time of execution, we need to bring the program from virtual memory to main memory. Okay, so swapping is nothing but bringing the program from virtual memory to main memory and taking it from again back from main memory to virtual memory. It will be more clear if we write. Let us assume that we have a program or process P0 in virtual memory. CPU will be presently executing that. But how much memory space I have available here? I have only this much of memory space. I have only this much. This memory is occupied. This memory is already occupied. So I have how much memory available here? Only this much of memory we have available. So if we divide, this concept will be details discussed in virtual memory concept. Just now, as of now, I will tell. See, memory will be divided into small size. Virtual memory will be divided into small sized blocks, that is called page, and similarly main memory will be divided into equal sized blocks, which is called frame. So this is frame and this is page. Page. Virtual memory is divided into equal sized blocks, that is called page, and whereas main memory is divided into equal sized blocks, that is called frame. The most important thing is frame size is equals to page size. Frame size is equals to page size. So page by page we can take the program part from the program and we can bring it to main memory. Why page by page? Because CPU is not executing whole program at a time. Maybe in the program, just one imaginary concept, program is divided into 4 functions: addition, subtraction, multiplication and division. So each one is present in this. Second portion is subtraction, third portion is multiplication, and fourth part is division. That is stored in one page. Just assume, it is not actually it will happen like that, just assume for understanding. So CPU immediately at the present moment want addition program to be present. It is in the beginning of the program. So what has to be done? That addition part has to be present in the main memory for execution. Next, which part will be referred by CPU? Maybe the second page. This is the first page, this is second page, this is third page of process P0. So addition part was present, so it was executed. Then subtraction part has to be present. If it is not there, it has to be loaded here for execution. Third part is what? Multiplication part. So next multiplication part should be loaded. Now when division part will be referred by CPU, division part will be referred means CPU will generate the logical address. Logical address means program's actual address when it is stored in the virtual memory. Okay, so let us assume this is this address is 10th address in virtual memory. So when it will be brought to main memory, maybe it is brought to 100 location of the main memory. So this is a physical address which is generated by memory, and this is the logical address, actual address what is referred by CPU. So from 10th location it is brought, then from some other location it is brought, and it is brought. Now when the CPU will refer for the instruction present in 4th page. 4th page cannot be brought here because 4th page is not, no space is free for bringing the 4th page. So what has to be done? One among these should be removed. So this removing is nothing but we are not actually removing. We have taken it from here to there. Now we will give it back to the virtual memory, and from virtual memory we will bring it to the main memory. Okay. So this what we are doing is the extra part, whichever part is not necessary now, that part we are giving back to the virtual memory. So this is called swap out. This part is called swap out, and this part is called swap in. So this is swap in and this is swap out. So swap in is nothing but when we are bringing it from virtual memory to main memory, that is called swap in, and swap out is nothing but when we are taking it back from main memory to virtual memory. So first should be which one? First should be swapped out. Sorry, first should be swapped out, then it should be swapped in, because there is no space. So first it should be out of the memory, space will be created, then this one will be brought from virtual memory to main memory. This will be brought from virtual memory to main memory. So this is nothing but your swapping concept. Demand paging also works in the same way. So whichever page has demand, that is there actually in 4th module, but always I told you we cannot distinguish much because it is always happening. Like it is always the concepts are correlated, interrelated. So this is nothing but demand paging. Which page has demand, that should be brought, and which page does not have demand. Demand means it is executed, so it will go back to virtual memory. So first is out, it will go back, so it is called swap out, this is called swap in. So this is all about your swapping technique. So now we will move to our next topic, that is contiguous memory allocation. So what is contiguous memory allocation? Before we discuss that, we will tell memory allocation technique is divided into two parts. Hope you can see contiguous and non-contiguous. Contiguous is divided into number 1 fixed partition, and number 2 it is variable partition. So even though I wrote dynamic, it is actually not dynamic, but it has little dynamism rather than this. This is also actually static technique only. Okay, so memory allocation technique is divided into two parts. One is contiguous, one is non-contiguous. Contiguous is divided into two, that is fixed partition and variable partition. Non-contiguous is divided into 4, that is paging, multi-level paging, inverted paging, segmented paging. Paging, inverted paging and segmentation itself is very important for exam. Fixed partition also some part is very important, that we will discuss one by one. So first we will see this is your contiguous memory allocation technique. I have noted down some points which I will go through after I explain. See, here we have taken two memory. You can see here we have taken two memory, both are actually of same size. How much is the size? 9 into 4 is 36. Here also it is 36. But how it is divided? See, here it is divided equally. Each are of 4 MB. So 9 partitions, so 36 MB. But here each partition size is not same. Okay, so this is 4 MB, this is 2 MB, like that, but total size is 36 MB and number of partitions here also it is 9 only. Both are fixed partitions, same memory size, same number of partition, but partition size varies. Okay, so we will now consider how actually contiguous memory allocation works for fixed partition algorithm. According to fixed partition, as I told, here it is both are 36 MB, both are 36 MB total. If you check, it is 9 into 4. Here also it is 9 into some different division. All divisions are not equal. Both are called fixed partition only. So if one process request comes for 3K, what will happen? According to that, it will be occupying one block from this available this. So this will be occupied. So what about this portion? This portion will be wasted. This part is actually called fragmentation. It is called internal fragmentation. So as 3K memory came and available memory is 4K, so 1K memory will be wasted. 1K will be wasted. Similarly, if 2K one more process comes, so 2K one more process comes, what will be the wasted space? Wasted space will be 2K. So this 2K will be called as internal fragmentation. So you can see here both the cases internal fragmentation happens. I will tell you once again what is internal fragmentation. When and before I tell you the internal fragmentation, I should mention one more thing. According to this fixed size, if total process size is 3K, all 3K should be continuously allocated in a block, free memory block. Okay, memory blocks are already divided into some parts, so whole program should be kept in a block. Like if I have a 3K process request, I cannot fit it to this, and I cannot divide it into two parts. That is the main difference between fixed this first one and second one, fixed partition and variable partition. I cannot break the process into two parts and put it in the two partitions. So I have to as a whole put it in the partition. So if my process size is 3K, I can fit it here, 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 here and here, but this remaining will not be fit for it. So and when my available partition is 4K, so after accommodating 3K process, this extra space which is getting generated inside the partition, that is treated as internal fragmentation. That is treated as internal fragmentation. Okay, so you have understood what is internal fragmentation. Now if there are so many processes entering to the system, I will consider a situation. What I have assumed is that pink color things are occupied by processes, and the blue color portion, that is wasted inside the block. Okay, so here together if you consider from this block 1K, 2K, like that, 2 plus 1, 3, 4, 5, 6, 7, 8, 9K space is completely wasted. I cannot fit one process in that. I can fit if the process size is less than 1, I can fit it here, but usually process size will not be less than 1K, so I can consider this as waste, but if it is so, we can accommodate. Okay, if whole process size is 1K, in that fragmented space also we can accommodate. Like here I have 1K free space which I am considering as fragmentation. If one process comes whose size is 1K, I can accommodate that process. I can accommodate 1K process in the fragmented space. This is my total partition. It is occupied, 3K is occupied, 1K was fragmentation. If one job comes with 1K, so we can fit it here, there is no problem, but we cannot usually because process size will not be so less, so it will be considered as a wastage. So internal fragmentation is when inside the partition I have some waste of space, like here this 1K, 2K, here it is 2K, 1K, here it is 2K because 2K is occupied by process, 2K is wasted. So this is internal fragmentation. External fragmentation is as a whole this full amount 2, 3, 4, 5, 6, 7, 8, 9k. This 9k is actually external fragmentation. Why we are considering this as external fragmentation? If one process at this situation, if one process comes whose size is 4k, even though I have some 9k or some space available, but I cannot accommodate it because I cannot break the process and divide. I cannot divide the process and fit 1k here, 1k there and all. So that is the main thing of this fixed partition. I cannot divide the process and accommodate. You should have questioned that why I have divided like that. Here the advantage is, if you have a 2k process entering to the system, you can put it here, you can put it here. Okay, so if this is a fixed partition, waste is more. Okay, because your 2k it will occupy and 2k will be wasted. Whereas if I have a variable partition, like partition size are different, so 2k process I can accommodate here to minimize the internal fragmentation. So this is actually the drawback, you can say, for fixed partition, but it is a main thing. Based on that only remaining paging schemes have been developed. So hope you have understood the difference between these two. In this case, less internal fragmentation will be generated, even though these both are same thing, that is fixed partition algorithm. According to fixed partition, so what are the drawbacks of fixed partitions are internal fragmentation, external fragmentation, and second point what I have mentioned is degree of multiprogramming is less. Degree of multiprogramming is less means we cannot utilize whole memory. Degree of multiprogramming is number of programs available in the main memory. Number of programs available in main memory will be less because lot of space will be wasted, and as we cannot divide the program, so we cannot use that fragmented space. Internal fragmentation is practically waste for the system. So number of process brought to the memory will be less, so degree of multiprogramming will be less. Actually degree of multiprogramming I have made a separate video that you have to go through. Okay, one more thing is this part I will consider first fit, best fit and worst fit. So according to this, just in brief I will explain what is first fit, best fit and worst fit, but this is separately discussed in other video which is already given. According to first fit, if I have a 2k process in this situation, I should put it in the first location according to first fit. Okay, best fit is obviously this one, but in for 2k process, best fit means where there will not be any fragmentation generated. So it is obviously best fit also. Worst fit is what? I should fit this 2k process to the largest available hole. Largest available hole is 5k. But if I am considering a process of 4k now, so 4k first fit is this one, best fit is among this anyone is the best fit, and worst fit is obviously this one. So how to solve the problem related to that we have already given separate video, because it is a very important question. They will ask you problems from that. So last topic I'll cover is variable partitioning in this video. So according to this, whole memory will be free. There will not be any partition before. Okay, so whichever process comes, that can be coming one by one and entering to the main memory. And you know, initially operating system will take some memory space, so rest of the memory will be free for all the processes. Okay, so let us discuss it. According to variable partitioning, except OS, whole memory will be free. Free in the sense maybe some other process would have entered, so that space will be occupied when we are considering, we are not having a fresh memory. So if you have a fresh memory, imagine it is free. Now 2k process comes, there is no partition, so you can accommodate 2k. Then when 4k comes, 4k you can accommodate. When 6k comes, you can accommodate 6k. Okay, so there is no partitioning, no internal fragmentation. Hope it is clear. But one more thing, I will just compare it with the fixed partitioning. See, already partitions are there, so 2k process will take, so this space, so this will be treated as internal fragmentation. Next, for 4k it will be completely occupied, so there will not be any internal fragmentation. Okay, then when 6k comes, what will be the situation in the fixed partition? We cannot accommodate because we cannot break the program. So in this case, if it is a fixed partition, we cannot accommodate. So this is the advantage of variable partitioning, or you can say dynamic partitioning with the this is the advantage over this fixed partitioning. You can consider a situation where 2K, 4K and 6K and 2K process came according to the fixed variable partitioning. And so 1K is the memory space wasted. Suppose this is the total memory. So 1K is the external fragmentation. There is no internal fragmentation. But in the case of deletion, like suppose this process is deleted here. Okay, now how much fragmentation I have? This is deleted. So 2K plus 1K, this will be the external fragmentation size. So at that moment, if one 3K job comes, at that moment, I have memory available, this is deleted, 2K plus 1K. So I can accommodate because 3K memory I have, but it is partitioned here and there. So this is a drawback of external variable partitioning, that is external fragmentation. So to recover from that, what we have to do, we have to go for the compaction. What is compaction? Compaction is nothing but collecting all the free space together. So this is nothing but the diagram of compaction, where what we have done is that 4K process we have as if copied here, 6K we have copied here, and 2 and 1 together we have joined, C2 plus 1. So now 3K is continuous. So compaction is nothing but a process of collecting the free space together and keeping it together so that we can avoid the drawback of external fragmentation in dynamic partitioning. Hope you all have understood up to dynamic partitioning. We'll do from the next, we'll start with some other video, okay, where we'll cover the rest of the part. Thank you for your patience.